but we have ZHENGYU, Dr. Liu with us for the next presentation as well. Accelerated construction of highway steel overhead sign truss through the implementation of U-bolt connection. Dr. Liu.
All right, thank you for having me present today. Again, this is ZHENGYU Liu from Iowa State University. I work for Bridging Center. So I have my graduate student Abdallah Amori with me. So he will give the presentation on a few slides during this presentation. So this research is all about accelerated construction of the highway steel overhead sign structure through the implementation of the U-bolt connections. We call this structure, usually we call this structure SOST structures. So here's a little background. So there are many states has used the U-bolt connection on the SOST structures. For example, our DOT used type A, two types of U-bolt connection. Type A is used to attach the horizontal truss to the vertical post. Type B was used to attach the screen to the horizontal space truss. So this was used, but the capacity of these U-bolts were not known for the design DOT design engineers, because these U-bolts are used in a different way that suggested by the manufacturer. So here was we did a phase 1 research to try to identify the capacities of these U-bolts. In the first phase research, we did both laboratory tests and analytical study. In the laboratory test, we test both type A and type B specimen in horizontal and vertical direction. And we also did analytical study to try to evaluate the capacity of these U-bolts in different loading direction, more loading directions. But eventually we found that in the analytical model, when we load this U-bolt in different direction, the failure mode with different loading direction are different. So then to get more confidence on our analytical results, we suggested that we need to do more static tests to verify those failure modes. So that's why we got this project, second phase project. The goal is to investigate structural behavior of the U-bolt connection and do more static tests to evaluate the U-bolt connection capacity failure modes through the experimental tests. And also then use the result to validate the prediction result developed in the phase 1 research. So to do that, we have a 5-task research. Task A1 is literature review, which was completed already. Task 2 is the lab test. The specimen we already purchased. They are ready in the lab for the test, but we are waiting for the lab availability at this moment. Task 3 is once we finish the task 2, the test, we're going to use the result to validate the prediction result in phase 1 research. And based on that, we probably develop some recommendation of how to use those results, which is task 4. And eventually we're going to drop the final report. So the next slide I will give to my graduate student, Abdallah Amori, and who did the literature review. And then after that, I will show you some. What we are doing on this topic is we are also doing a field monitoring on SOST structure. So after Abdallah's presentation, I will give you some information about our field monitoring progress. So Abdallah.
Thank you, Dr. ZHENGYU. So as we know, like the highway sign trusses and overhead support structures are essential components for transportation network systems, and several studies have been conducted to investigate the causes of fatigue failure in these structures. So I will present in the following literature review a summary about these studies. For example, the first studies is like the influence of thermal loads on bridge type overhead truss support structures was investigated through field monitoring and finite element modeling. And the results of this research paper was that the fatigue life estimates were significantly shorter than expected service life of the structure. And the authors in this suggesting that thermal loads could be a significant factor in the fatigue failure. The other research paper, the wind loads. The research board report investigated the wind loads on dynamic message cabinet, or DMS, and the behavior of the supporting truss. And then the report included a computational fluid dynamic, or CFD, study of wind loads on DMS. And then the report that found that the wind loads on DMS can cause significant vibrations in the supporting truss, which can lead to a premature failure due to fatigue damage. Now, the third study, fatigue of steel bridge infrastructures. In this one, the authors provide a comprehensive overview of the fatigue behavior of steel bridges. And then the authors discuss the causes of fatigue failure and various methods to prevent it, such as using maybe high strength steels or designing the bridge to minimize stress concentrations. The fourth literature review reference evaluation of aluminum highway sign truss. In this research paper, the authors evaluated the performance of aluminum highway sign truss under both wind and truck gust loadings using field monitoring. For the sample rate of field monitoring collection data, the authors used 100 Hertz, and the gauges were 350 ohm. And then the study found that all of these new sign structures satisfied the current AASHTO specifications, but the recommended drag coefficients was smaller than values that determined from wind tunnels tests. And the last one, it's the investigation by Hackenderbeck et al. In 2009, investigated the cause of sign truss failure that occurred in Dayton, Ohio, on September 11th, 2006. And then the research was on the field monitoring of traffic-induced vibrations and finite element simulations. And then the conclusion of this research report was that the high cycle fatigue or the high cycle fatigue of the cord with diagonal welded connection was the main cause of the truss failure. And then the study suggested that the enormous quantity of response cycles that a bridge mounted heavily traveled route accumulates over its service life could exceed anything currently considered in the design codes for such structures. Now, the main summary of the literature review is like the steel overhead sign truss studies have been conducted. However, the fatigue capacity and performance of U-bolt connections basically are not fully understood yet. And then the current design loads used in many states could exceed the design capacities of the current U-bolt connections, indicated there is a need for further investigation. And also the last one is like the use of computer modeling, like finite element modeling, has not been fully utilized in evaluating and validating the U-bolt connections as identified through literature review. Thank you.
All right, thanks, Abdullah. So next, I will give you some information about our field monitoring progress. So the goal of doing this field monitoring is to monitor structural behavior of a SOST structure. With that, we can evaluate how much forces were transferred from those U-bolt connections. So to do that, we have three types of sensors on our field monitor's SOST structure: anemometer, which is used to measure the wind speed, wind direction, and strain gauge, and thermocouple. So the anemometer and strain gauge were collecting data with 100 Hertz, and thermocouples were collecting the one data per 10 minutes. So the entire monitoring will continue for more than 12 months to collect the data from over 1 year period. And the data collected from here will be analyzed using rain flow counting method to calculate the effective stress range. So here's the SOST structure on Highway I-35 that we are the SOST structure that we are monitoring. So here's the instrumentation map on this structure. So the anemometer was put on top of the horizontal truss to measure wind direction, wind speed, and we have two instrumentation sections. Instrumentation section 1 is on the horizontal space truss, and there are 10 strain gauges or 12 strain gauges were attached to the horizontal cords to measure the strain that in the longitudinal direction of those horizontal cords. And the second instrumentation section is on the vertical post, that where we have 4 strain gauges that on the vertical post to measure the strain in the vertical direction. So here's our data acquisition system. The anemometer and thermocouple were connected directly to the logger, and 16 strain gauges were connected to the 2 multiplexer, and those 2 multiplexer were connected to the logger. Here's some fieldwork photos grounding the horizontal steel cord before the installation of the strain gauge. The setup of the anemometer on top of the space horizontal truss. Here's the strain instrumentation on the vertical post, the logger installation. So we started instrumentation, but we haven't finished it yet. So we still have 6 strain gauge that need to install to the horizontal space truss. So for our next step, once our lab is available, we're gonna set up for the test U-boat capacity test, and then conduct a static U-boat static test. And we are also meanwhile we will finish the field monitoring instrumentation work and start collect the data and analyze the data. So that's everything that we have so far for this project. If you have any question that we can talk about.
Thank you very much, Dr. Liu, and thank you, Abdallah, for your presentation. Let me see. Okay, the question is on your monitoring. It's asking, how does the field monitoring benefit the evaluation of the U-boat static capacity?
Yes, as I said, so we are doing the lab test. The proposal research on the proposal that said we're gonna do the static test. That's all about the capacity of this U-boat, but we are not sure what's the need for the capacity for this U-boat connection on a real SOST structure in the field. So the reason we do this is that once we have the wind direction data, wind speed data, we can evaluate the pressure on these structures, and by monitoring strain gauge monitoring, by using those strain gauge, we can actually calculate the load that transfers through those U-boat connections. So once we know the exact load on those U-boat connection, we can make a comparison with our lab test results. So we get more confidence for when we develop the recommendation for how to use our prediction result. We have more confidence on these results.
Okay, and but you mentioned comparing the field monitoring with the test. I think somewhere in your presentation you said that you're going to use also finite element modeling.
Yes, that's what we are thinking right now. So we either will do a hand calculation, or maybe if we see that there's a need, we will do maybe a finite model and maybe use those strain data to calibrate the model to see so that we can have a better result to more direct view to see what's the loading transfer at those U-boat locations.
You are right. I think that field monitoring will help a lot in the finite element model.
Right, correct.
And one tricky question, you mentioned a couple of times that lab is not ready for testing. A question is asking, when would that lab be available for you?
That's a very good question. I think maybe my colleague Justin Dover can help me answer this question. Justin, I'm not sure if Justin's still on call.
You can. I'm not sure you can hear me or not, but
yes, we do.
Okay. Yeah. So right now, I mean, the advantage we have of having a lot of research is that we have a lot of research, but what that complicates on our end is lab availability. So we have a queue of projects ongoing, and it's likely that between this project and our previous project we presented, it'll be probably the next 3 months. We'll get into the lab and then continue our lab work through the end of the year.
Very good. Thank you very much.